Indeed is the #1 job site. If you've used us, if you don't know us, just walk outside to the 6th Street, the tallest tower. That's who we are. We are a job matching and a hiring platform in over 60 countries, 28 languages. We have over 3.5 million employers using the platform, and unique visitors averaging 350 million plus every month. The job seekers get access to our platform for free, which is great. We try to keep it this way. We remember everything we do at Indeed is for a job seeker. Even when they are not there, we think about how this impacts a job seeker day to day. They are able to use our platform, post their resumes, research companies, and leverage it so they can get close to hire. Our mission is simple. We help people get jobs, and that's what we say every time. We even have our Scrum sessions, if you will. So we remember what is our mission and who we are serving at will. My name is Gayatri. I'm part of the core infrastructure team that scales and does all the platform engineering. I heavily work on NoSQL, particularly Mongo and Kafka. And this is...
My name is Ryan Merriman. I'm an architect in trust and safety, and I work with Kafka.
So who we are, you got a little intro, but if you see the platform trust and safety depends on another platform, the core infrastructure, which is sort of like your distributed computing and storage environment. My team is responsible for maintaining the centralized management platform, giving paid paths for all these product teams who have to engage with us for various workload shapes and performance profiles. We have to address their growth, their size, their ambition to grow and scale at certain times of the year. And we have to meet compliance and keep the platform secure. Ryan's team has a mission to keep our users and employers safe when they are using our hiring platform. So we want to reduce risks from fraud, detect fraud, and proactively engage in trust and safety measures. We also use agile processes to keep our policies updated. If there is a change in GDPR, for example, we would embrace that change, part of the platform. Our segments, 4 major corners we always visit is the job seeker, the employer, what segmentation of job seeker or employer we are focused, and the society, which is the geographical location. So every part of geography brings interesting sets of problems to serve for and localize. We use several different kinds of logs and aggregate them using Kafka. This is why our choice for Kafka happens to be the reason. We use Kafka because it's an append-only, immutable log of all the activities going on our hiring platform. We aggregate website logs, identity logs, every interaction our users have with our platform. Also the application tracking segments where we have plugins or interactions and integrations to our job seeker platform. We also have transaction logs, so we can stagger Kafka being like the buffer for the frontline experience, which then aggregates back into a backend that gets synced back through a change data capture implementation to our analytical platform. In the backend, we are able to do fraud detection, recommendations, and also build out a contextual knowledge so we can recommend better suggestions or also learn properly how we react to fraudsters. We heavily use ML and AI for those purposes. So why do we use Confluent? Indeed uses Confluent Cloud. We are 100% a Confluent Cloud customer. The reason is we wanted to get rid of our operational toil of running Kafka in a distributed scale and focus on the data and the intensive use cases we have with Kafka. We have sources in several platforms, the data analytics platform, the databases, your SQL and your NoSQL, the CRM systems we use for marketing. We also have all these monitoring and management integrated to Confluent. And for scale, we have instrumentation with IAC, like Terraform, and we go and engage in scaling up and shrinking down based on our workload shapes and needs. The data is sunk into a data lake, which is then available to all our product teams and people interacting with them. More data scientists who want to go and model and build out ML pipelines. And we also have a company-wide event store. So every interaction, every application at Indeed writes to a company-wide event store. We call it log repo. In terms of developer productivity, you can see building each of these pipelines, front end or back end, we have to instrument some way for these people to self-serve. So we don't have to have manual processes where people are running ETL or ELT or coming up with batch interactions. So we have gone and done self-service enablement for our developers and reduced their time interacting with these different pipelines. Apart from this, we have increased with Confluent and the metrics we aggregate the observability to these interactions, so they are able to understand over time how the product adoptions are happening and how they should think ahead of scaling and sizing requirements. The security and auditing capacities are also exposed to the developer who can go and self-serve and see every interaction to their Kafka topic and Kafka environment. We are big believers of push green, which was a concept actually introduced by Google. We continuously deploy to production and we push on green. And we are also all about breaking things faster in QA, of course, and staging, near prod, and learning from that experience really quickly. So heavy Dockerized environments, before it goes to production in Kubernetes at scale, we test it quickly and have QA checks and processes. And now Ryan will talk to you about trust and safety.
Thank you, Gayatri. My favorite way to describe our team is that our OKRs are constantly fighting back against us. OKR stands for objective and key results. The other teams, they set their OKRs, they plan for their OKRs, they work towards their OKRs, they achieve their OKRs, but not us. We're in a constant battle against fraudsters. We're constantly playing a game of whack-a-mole. A fraudster will pop up out of a hole over here, we'll whack it down, they'll divert their effort over here, we'll smack it down, so it's constantly smacking moles down, coming out of new holes. In this presentation, I will tell you a little bit about the use cases and problems that we solve, give you some context on our team and how they're structured. When you're playing whack-a-mole, you have to move fast. You don't know where the mole is going to pop out of, so you got to be there to smack it. Maybe over here, sometimes you're smacking it two at a time, same time. So you got to move fast, and that's what we do. I'm going to tell you about how we move fast, some of our strategies to do that. And then later in the presentation, I'm going to highlight a couple of interesting use cases where we put these into practice. I'll set up the use case, tell you a little bit about how it works, and then we'll dive deep into the architecture. I know that's what you want to hear. I'll deliver the goods. And then we'll talk about something we learned along the way. Hopefully some of these lessons learned you can use to improve your architecture, and most importantly, the impact that our efforts had. Anybody know what the 3 V's mean? Anybody heard of the 3 V's before? Variety, velocity, volume. You'll notice how these 3 circles all overlap on this slide. Our team is squarely in the middle because we have to deal with all 3 of them. Velocity and volume, I feel like this has gotten easier to solve over the past 10 years, past decades, because of Apache Kafka, because of the amazing ecosystem Confluent has created around that. So we deal with volumes, we deal with billions of events, not crazy big, but still big enough that you have to design for it. We are definitely have real-time requirements, so real-time is very important to us. We want to stop fraudsters ASAP. But I think our biggest challenge is variety. We have hundreds of different event sources that we consume from. They use different serialization formats. They use different message brokers. We have legacy RabbitMQ. We have SQS. We need to work with protobuf, we need to work with JSON, we need to work with Avro. So that's challenging, handling all of these different data sources. We constantly have new use cases. A lot of our use cases are experiments, so we need to go fast. We need to quickly learn, decide if we want to take it further. And new use cases are always popping up constantly. Our engineering teams, we do not have a dedicated Kafka team. Our engineering teams are structured by product domains. This means that our teams need to be good at everything because they're generally building things end to end, and this includes Kafka. We're big on tools. This is how we help our teams go fast and build things quickly. Two tools I'll talk about today. One is a GitOps workflow that we use to provision Confluent resources. This allows our teams to quickly create what they need in Confluent, topics, etc. And we have a microservice library that we use to help our teams accelerate their development, focus on business logic and not focusing so much on the common concerns when writing a consumer. Support and knowledge is very important to us too. This is, whenever we started our Kafka journey, I was doing most of this, and I quickly became a bottleneck. I quickly realized that I was answering a lot of the same questions directly to people. Other people had built competency and were, in many cases, smarter than me and more experienced with me than Kafka. And so creating a Slack channel was huge. That allowed us to give people a place to come to get answers about the library, get answers, design answers on common design problems. And of course, we take pride in our documentation in Confluent and README, so we take that seriously and we keep it up to date. The point of all this is that our engineers, they don't need to be experts, or they don't need to have previous expertise in Kafka to move fast because we help them. Okay, first tool I'm gonna go over is our self-service GitOps workflow. This is a fairly common thing in Indeed, but it's crucial for us because we have lots of topics in our cluster, probably around 70 or so, and it's not always obvious what people need to create for their use case, and so we help them with that. This is a high-level diagram of how it works. We use VCS integration in Terraform to integrate GitLab and Terraform, and what this means is that when we create a merge request, a plan is run in QA and prod. It gives us a preview of the outcome that will happen if we apply this change. When we merge it to main, it actually creates the resources in Confluent for us. Like I said, pretty standard thing in Indeed. We use the Confluent Terraform provider. I've got some links in the speaker notes if you're curious on how to actually use these. And then we have a little bit of secret sauce in that we have a Python script that we use to make this easier. We looked at using a Terraform module, but the downside of that is people still have to have Terraform knowledge to be able to use it. So we favor an interactive Python command line interface to do this. It prompts users for information, a topic, name, partitions, some things that might not be obvious to them, like who they want to give permission to read and write from the topic. And it's worked great so far. An unintended benefit from it is that it makes reviews much easier for us. Because when we're reviewing somebody's merge request, we have confidence that it's correct and the style is correct because it was generated automatically. And you'll notice that we manage topics, ACLs, API keys, service counts, so pretty standard stuff. This has allowed our engineers to create these resources in as little as 5 minutes. Usually the most time is spent waiting on somebody to approve. And that happens pretty fast because we have a channel that people can ask for help in. All right, the next thing I'm going to talk about is our library. This was created out of necessity, where we had a use case. We needed had different teams working on a use case. They all needed Kafka consumers. And so instead of all of them creating these consumers in a silo, we created a library with a lot of the best practices baked in, so they didn't have to think too much about what they're doing. All right, on the left, you'll see within the library, we use some common dependencies, some common libraries. Apache Avro, we were very opinionated about that, so we require Apache Avro to use this library. The library would be much more complicated if we did not do that. Spring Boot is the common development framework at Indeed, so we use that. Everybody knows it. Everybody is familiar with it and knows how it works. Learning curve is very short for a lot of people. A lot of times we are doing enrichments or taking action, which involves an external service call. And for that reason, we picked Kafka Reactor for that because of its non-blocking I/O. So that's worked pretty well for us. And then, of course, instrumentation and observability is a first-class citizen in our library. So that's something we add. Many times that's an afterthought for engineers that are trying to get things out the door quickly. And so we bake this in so that we guarantee that we have an observable service. Up at the top, we have a template that we've created that allows engineers to quickly spin up a new repository. It's fairly easy to add to an existing application, but generally we recommend spinning up something brand new. This thing comes with everything you need, including the library, dependencies, examples, which have actually been pretty useful because it guides people on how to use the library. And so we use this thing heavily. Below, you'll see an example box. So we have an example deployment that is real, that is deployed to QA and prod. It contains a simple example that works out of the box so people can check it out, play with it, demo it, and also test new features as you promote it to QA and prod. You'll notice there's a local Confluent cluster box at the bottom. That is our development environment we use. We use this across Indeed. It's based on the Confluent Docker images, and we love it. This example pipeline is the exact same that we use for our real applications. So this blazes a trail for people to deploy a real consumer to production. So let's dig a little deeper into the library. These are the various roles and responsibilities that the library maintainers, which is the community of people in trust and safety, and an engineer that is working on a use case. We provide, the library maintainers provide configuration. This is something that's easy if you've done it a couple times, but can add a lot of friction to the development process if you've never done it before. Instrumentation, like I said, first-class citizen, we take that seriously. We have declarative tagging, so a lot of times you can tag metrics, traces, logs, without needing to add any code for that purpose. It makes the code much more readable. Usually that's the case, sometimes it's not. And we have integrations with common Indeed systems. Datadog is our preferred tool for observability, and we have a custom homegrown event store for logging and analytics, and it's integrated with that too. The goal of it is for engineers to only focus on writing the business logic while the library takes care of the boilerplate, integrations, everything else, kind of like AWS Lambda. All right, let's talk about some use cases. These are two use cases that I think are fairly complex that had a huge impact, so I'm excited to share them with you. First up is impossible travel. This one has a special place in my heart because I was able to contribute to this one. The team was gracious enough to let me do some coding, so I love this one. Here's how it works. A user is interacting with Indeed as they normally would. A fraudster could be across the world. Somehow steals their cookies. I'm not going to tell you how they do that. And they can impersonate this user and take over their session and cause damage. In trust and safety, we call this an account takeover. It's very likely that a fraudster is not sitting next door to a user when they do this, so we can take advantage of that fact and measure the distance between the session events we get. And if we determine that they have traveled an impossible distance, then we can mark them as fraud and take action. Smacking moles worldwide. Okay, let's dig into the architecture. This is how it works under the hood. Like I said, we have some session events that we consume through Confluent. This thing is big. It's 1 billion events a day. that is too big. Our downstream services are not going to be able to handle that volume. Scaling them up to that volume would be very expensive and difficult. So fortunately, there's a signal that we can use to filter out events that we don't care about and leave only events that we do care about, in this case, employer events, because this type of fraud happens with employers. We have a service that provides this signal. Unfortunately, that service has a 200 requests per second limit, so we also cannot throw 1 billion requests per day at it. To do this, we use a 2-layer cache. We use a Redis cache for longer TTL. We use an in-memory cache with a shorter TTL. The in-memory caches do not need to be as big because we're partitioning by the same key that we're using in the cache key. So our in-memory cache is partitioned across our instances. The Redis cache is very important. We learned we didn't do this at first, but we quickly learned that whenever a pod is killed or a consumer is restarted, it needs to rehydrate that local cache, and it puts a huge spike on this service. So putting a Redis cache in place to solve that. Next step in the process is we enrich it with geolocation information. We use DynamoDB to store state to compare the current event with the previous event. This is how we detect impossible travel. We enrich that, send it downstream, and then we use a rules engine to write rules against that. The purpose of the rules engine is it gives our moderators flexibility on the distance that they're using to say that somebody has impossible travel, incorporating other signals into the rule that they may have about the fraudster. Important lessons learned on this one was that to filter early and often. That's one of my favorite sayings in the big data world. And this is definitely the case here. We could not have done this. We might have been able to scale it up, and we actually did end up scaling up our rules engine to handle this, but the combination of filtering and scaling up was necessary for this use case. And another issue that surprised us a little bit was that ordering is definitely important for this, because if we get events out of order, it would be a negative. Depending on how out of order they are, we're not able to properly compare them with each other. We made the mistake of not oversizing our partitions. So we sized it for what we thought in the beginning, we undersized it, and when you increase partitions on a topic, events are temporarily reordered, and so this was an issue for us. It caused us some operational pain because we had to deal with that. The impact was huge. I'm very proud of this one. That is a massive reduction in fraud, and it's one of the most effective things that we've done. You'll notice on the last one there was a slight increase in live jobs. The purpose of this is not to highlight how much we improve things, but that we did not make things worse. That is something that we commonly measure in our team is good actor harm. In addition to the effect we have on fraud, we don't want to harm good actors. That's very important to us. Okay, the next one is message moderation. This one is challenging. We have now introduced a social engineering aspect to this. Fraudsters can directly message users. They don't even have to leave their holes, but we still got to smack them. To do this, we use a combination of both a rules approach and a machine learning approach. We ingest message data along with various other signals that we know about a fraudster. And then the rules engine approach and the machine learning approach work together. The rules engine, rules are written by humans. The patterns are fairly obvious. They need to do this quickly to react to things. The machine learning pipeline may recognize patterns that are not as obvious to a human. Okay, here's how this one works. This one was difficult to fit on a single slide, but see how it goes. We use a feature store for this use case. The reason that we use a feature store is we need to do real-time evaluation. So we want to make predictions in real time as soon as possible. The way a feature store works is you store data in 2 different ways. You store it in an offline store. In an offline store, you keep track of every single event that has ever happened over time. This is used by data scientists to train models and experiment. The other part of that is an online store. An online store keeps the most recent version of an event, and this is used to make predictions. One of the limitations with the feature store that we chose was that it did not support partial updates. And so we had to architect our way around this. This is challenging because the signals that we're ingesting are not together. They're coming from many different sources, and so we need a way to join them together. Our first attempt at this was to just use the online store to look up features from the online store, update it, and put it back. This did not scale well. So we employed a Redis cache to do this. You can tell we like Redis and Confluent. You'll notice that at the beginning we have a universal schema. This was an optimization we added later because we found that reading from Redis concurrently was a bottleneck. And so the point of doing this is to get all events into the same topic with the same partitioning scheme so that the keys are all in order. By doing this and having the keys in order, we're able to make writes to Redis. We're never doing it at the same time. So every write we're doing, we don't need to mess with distributed locks. Distributed locks are bad. You should avoid them if you can. And this made our pipeline much, much faster. After that, we've got an enriched event that we can write to the online store and an offline store at the same time, make our prediction, ingest into the rules engine, and moderators can use the output of this model prediction in their fight against fraud. All right, this was a challenging one. We didn't nail this one on the first try. This took several tries to get it right. Partial updates, like I said, are challenging. So if you have that limitation on your data store, be aware that you are going to have to handle that in a likely complex way that we did. We also learned that using the same data in an offline store and an online store is very important for model accuracy and recall. I think initially we used a different similar data source and we did not get good results. So adding a feature store that allowed us to do this was very important. And event ordering is also very important here. We were able to use partitioning and partition level ordering to solve our concurrency problem. Again, like Impossible Travel, the impact of this one was huge. We had a significant reduction in fraud exposure for our test group, and I think reducing fraud exposure by 51 is awesome and amazing. So those are the use cases, and I'm going to hand it back to Gayatri. Thank you.
Yeah, so as you saw, the choice of Kafka was right and using Confluent was right because event order matters and attacking the fraudsters who are near real time interacting with us and recommending is important. So this is why we use Kafka. So then KSQL comes into picture for your interactive queries and how do you limit rate limit on these bulk message updates, right? And so as you heard, the problems with Redis was if there was a pod restart, your cache has to be warmed up again. And if there was something disruptive that happened to the in-memory cache, there's lots of events to go and re-ingest and come back. So KSQL was a perfect solution. We found we were able to handle the low latency requirement and handle over 40K events every day and make it possible for our downstream consumers to have over 200 interactive queries running against our KSQL clusters. We are just at a bare 8 CSU, if you're familiar with the Confluent Cloud KSQL unit. We're still able to handle this much volume and variety of traffic. And we scale on demand too, if there is a burst in traffic. One thing that didn't work was there's still this open, if you go to KSQL, you will find this open bug where there is like a long running query, interactive query, leaving a pod in a shutdown state, right? It's not been addressed in the open source version, but since we are partners with Confluent, they were able to deploy a hot fix for us, and we were able to get on with our business about handling this problem. Why did I highlight that? It's important, as you know, with open source technologies to experiment, but if you're talking about billions of events and handling scale, you need a partner as Confluent. The other thing I wanted to mention was just JVM settings and DNS. Who knew DNS is always a problem? Yes. So yeah, some lessons learned with this was observability is key. When you're going with a managed partner or managed solution such as Confluent, what you have to improve is you've given your control plane away for the managed vendor to go and maintain it for you. You have to increase your observability into this managed platform, and that's what we have had with Confluent. We have been able to ask for aggregated metrics, get targeted notifications and interactions with our cluster resources and different components we use in Confluent Cloud. We have tagged resources that alert us based on cardinality, and we get granular metrics. So not just cluster level, we get it at partition and topic level, and we are able to use the cardinality to our advantage to size and scale and make decisions about costs. Apart from this, we have built a strategic partnership with Confluent. We have regular office hours where our developers can attend and ask for open issues. Our CS does and our account team engage with us regularly to address open issues from the support cases we have filed. We have deep dive sessions if there is an upcoming feature in Apache Kafka or KSQL or Flink. We want to engage and understand how this is done. We spend time with Confluent. We also have professional services where we don't have the resources at that particular time, but this is a very blocker issue. We can leverage Confluent to go and solve this problem for us. We conduct quarterly business reviews, so kind of a look back. What have we accomplished together past quarter? We do that. And we do support sync-ups, so we can improve the quality of support for the managed platform. And we conduct routine audits, so we can forecast growth of this managed solution and conduct architecture reviews, so we understand the patterns and anti-patterns of our Kafka usage at Confluent Cloud. With that, I wanted to thank for your time. I know this was just before dinner. Thanks for listening to us.